So this coding problem has that dreaded hard rating. But you know what? Don't let that label scare you off, because hiding inside this puzzle is a really elegant solution, and it reveals a powerful secret for solving all sorts of complex problems. So let's crack this thing open and see how we can turn a tough challenge into something that's actually surprisingly simple.
All right, first things first, let's not even think about code yet. Let's just treat this like a game. We've got a board, and we just need to figure out the rules to win.
And here it is. This is our puzzle board, a grid of numbers. You can kind of think of these numbers as being like different elevations on a map. Our goal? To find a very specific kind of path through this terrain.
And here's the core mission, the big question we need to answer. If you can start on any number on this grid, what's the longest possible trail you can make where every single step you take is to a bigger number? That's the puzzle we're here to solve.
Okay, so like any good game, there are rules. Before we can even think about finding the solution, we've got to know exactly how we're allowed to move around this board.
The number one rule, the most important one, is that we are looking for a strictly increasing path. What does that mean? Well, it means if you're standing on the number 6, your very next step has to be to a number that's bigger than 6, like an 8 or a 9. Moving to another 6? Nope, not allowed. It has to be strictly greater.
And how can we move? Well, it's pretty simple. We can only go in the 4 main directions: up, down, left, or right. That's it.
And there are a couple of really important don'ts to remember. First, no diagonal moves. And second, you have to stay within the boundaries of the grid. You can't just step off the edge and reappear on the other side. Stay on the board.
So keeping all those rules in mind, let's look at the answer for our puzzle. The longest path here actually starts at the 1 in the bottom row. Then it goes up to the 2, then up to the 6, and finally to the 9. That gives us a path with a total length of 4.
All right, so how would we actually write a program to find this? You know, the first idea that pops into your head is often the simplest one, but as we're about to see, it's also the slowest, by far.
Our first instinct might be what we call a brute force attack. Just try everything. We could start at that top left 9 and explore every single path we can find from there. Once we've checked all of those, we move to the next cell, and then the next, and we just keep doing that until we've started a search from every single spot on the board.
And the algorithm we'd probably use for this is called a depth-first search, or just DFS. It's basically perfect for this kind of task. It just means go as far as you possibly can down one path, and when you hit a dead end, backtrack and try the next path.
But, and this is a huge but, there's a massive flaw in this plan. Just imagine, our search starts from the number 2. It explores and finds the path 269. Awesome. But then, a little later, our search starts from the number 1. It finds the path 1, 2, and then it has to recalculate that exact same 269 path all over again. All that work is completely wasted, and on bigger grids, this problem doesn't just get a little worse, it gets exponentially worse. And that huge, glaring inefficiency is exactly what leads us to that classic aha moment. This is the key insight that's going to turn our slow, clunky approach into something incredibly fast. The whole idea, the big breakthrough, boils down to one simple but powerful question. What if we could just remember our work? What if, after we figure out that the longest path from the number 2 is 3 steps long, we just write that down somewhere?
Well, this idea actually has a fancy name: memoization. All it really means is creating a memory, or a cache, to store the answers to questions we've already answered. That way, the next time we're asked the same question, we just look up the answer instead of doing all the work from scratch.
And I mean, the difference is just night and day. On one side, you've got the brute force search, just spinning its wheels, doing the same calculations over and over. And on the other, you have this optimized search that remembers its progress and just zips right through, fast and efficient.
Okay, so we've got our tools. We have our search algorithm, DFS, and our optimization superpower, memoization. Now, let's put them together and see what this elegant solution actually looks like in action.
So once again, we start with our input matrix. This is the landscape we're exploring.
Now, to make memoization work, we create a second grid, our cache, that's the exact same size as our input. We'll start it out full of zeros. This grid is going to act as our program's memory, its little cheat sheet, where we'll store the answers as we find them. Here's how the logic plays out. When our search lands on any cell, the very first thing it does is check the cache. If it sees a number there that isn't 0, it means, hey, we've already solved this, and it just returns that saved answer instantly. No more work needed.
But if the cache is 0, then okay, we do the work. We explore all the valid neighbors that have a bigger number. We figure out the longest paths from each of those neighbors. Then we take the longest of those paths, we add 1 to it for our current cell, and this is the most important part, we save that final number in our cache before we're done. That way, we never ever have to calculate it again.
And we just run this process for every single cell in the grid. Thanks to our cache, the hard work for any given cell only happens once. By the time we're done, our cache is filled with the longest path starting from every cell. So, the longest path in the whole matrix? It's simply the biggest number we find anywhere in our cache.
So you might be thinking, okay, cool puzzle, but why does this really matter? Well, because this isn't just about one little coding problem. It's about a fundamental, incredibly powerful pattern for solving problems.
So, just how much faster is this new approach? Honestly, it's hard to overstate. The brute force method's runtime blows up exponentially. It becomes totally useless for even moderately sized grids. But with memoization, the time it takes is directly related to the number of cells. We basically just have to do a little bit of work for each cell, just once. That's a monumental, game-changing improvement.
And that brings us to the real key takeaway. This pattern, taking a search and giving it a memory so it doesn't repeat itself, is the core idea behind a huge computer science concept called dynamic programming. It's a strategy for solving massive problems by breaking them into smaller pieces and making sure you only solve each little piece one time. And you see this idea everywhere, from how your web browser caches data to load pages faster to how complex financial systems run their calculations.
So, I want to leave you with this question. We just saw how remembering results can find the longest path in a grid. Where else could you use this idea? Think about it. What repetitive tasks are slowing down your own work that could be solved once, written down, and then just